body, I will spoke about
Yeah, so I will talk about new studies about starbursts and the multi-messenger implication. I worked it with my colleagues in Naples. So here just a first expectation done for starbursts when much before the Fermilab and ice cube observation. So when it was not easy to constrain what can be the spectral property of the sources at high energies, and just reported this for a reason. And here in this slide, I want to say that looking at the ice cube diffuse flux measured, that it's possible to fit in a direct way the energy part of the spectrum, looking at the blazar and accelerator. This is the case extrapolating TXS 506 plus 056 to an entire population of blazar, and see that we have a room at the lower energy for reservoir type object. So in this case, putting together the galactic contribution with most extragalactic reservoir, probably we are able to fit this part of the spectrum. And also here in this slide, I reported one of the reasons why also starbursts come up in the community. Just that's one case of NGC 1068 that is close by starburst that was observed as an hotspot in the northern sky of ice cube. And we see here that when we look at the TeV neutrino observer in the direction with this object, it's kind of hard to justify all this flux just through a starburst component. And basically, there are several papers and work who had an IGN activity, so just to fit the entire flux measured. So that's another. Okay. So for when we look to this kind of object and when we want to extrapolate the contribution to the diffuse sky, we can play it together with the neutrino from the ice cube and with the gamma ray from Fermilab. And we also look to the extragalactic gamma ray background that is measured by Fermilab, and there are different work that try to fix and put a bound for the different component of the AGB. And we have some prior that we should take into account, like the one of 2016, both about the resolve point like contribution inside of this measured spectrum by Fermilab. And also, it's why it's important to look for starbursts, because those objects are a very high star formation rate in the central few hundred parsec of the galaxies. So and also containing cosmic rays in this part, we have a very nice environment for the proton-proton interaction. Therefore, we can expect more hadronic production for this kind of object. And of course, they are very abundant. They are not so luminous in gamma rays. And as I said, the star formation rate is from 10 to 100 times what we have in the Milky Way. So when we try to describe this object to a calorimetric scenario, so assuming that in the central part of the galaxy, we have a T loss greater than the escaping time, and we can play with a different parameter of the sources, like the Pmax inside of the galaxy, so the maximum energy reached by accelerated cosmic rays inside of the galaxy, the alpha that we observe in the gamma ray from the few known sources from Fermilab at the gamma ray energies, and also the rate of supernovae remnant, and also then therefore also the density of the interstellar medium. And generally, M82 is taken as a prototype because it is a well-known, and we have data from Fermilab and from imaging Cherenkov, like in this case, Veritas. And we can use, we should use also a physics of cosmic rays to describe what happens inside of the core of this galaxy. So we should take into account the time losses, the advection, and the diffusion inside of the galaxies. And here, what happens if we take into account not only one prototype, so not only M82, but we take all the 12 known SBG from Fermilab, and we look at the distribution of the alpha from this object. And we see that when we extrapolate this kind of contribution, so using the colorimetric approach to describe the expected gamma ray and the expected neutrino, and then extrapolating this to a possible diffuse component, we see that we obtain something different than using just M82 as a prototype. So you see here that for gamma ray, you basically, for the diffuse gamma ray, you basically obtain something very similar, but exactly, so here you see that there is no much difference for the low energy part also of neutrinos. So you have in orange gamma ray and in blue neutrino. And then you see when you move on the high energy part of the spectrum, how can change the expectation when you use so a blending, so a distribution of different alpha from the known SBG, and using just one of them as a prototype. So in this case, we did this multi-messenger fitting of gamma ray and neutrino components, and this is interesting because, of course, this kind of approach and this model leave space at high energy also for other astrophysical objects. And here I reported the different ingredient that we use for this multi-messenger fit. So basically for the diffuse gamma ray, we use the SBG blazar and radio galaxy component. And for neutrino, we use the blazar and the SBG component. And we put together different samples. So in this kind of fitting study, we use the two samples of IceCube, the as a sample and the cascade, and we use the AGB also, as I said, from Fermilab. And we take into account also the prior on the resolved source on the AGB. And what we obtain is basically here you see the expectation, taking into account here the ESE sample and the Fermilab AGB. And here take into account the cascade and the Fermilab AGB. And you see the 1 sigma possibility spectrum that you take out, that it comes out both in gamma ray and neutrino. And it's interesting that was the old prototype scenario taking into account only M82. That's the new scenario with the blending of the known SBG from Fermilab. And you see here, it's interesting because we closed also the parameter at 1 sigma, the possibility of the Pmax inside of those galaxies. And you see here that we have a preferential Pmax at around tens of PeV. So that's another important information that comes for the reservoir in general, and especially for this kind of sources. And we can see here that at 2 sigma, you can account up to 40% of the total IceCube flux. So basically, then here in this slide, I said that are too few the SBG observed by Majin Cherykov, and we should expect much more for the incoming telescope like CTA, that because it's very important for us to extend the spectrum of Fermilab at higher energy to constrain more the parameter of the colorimetric scenario. And here we did the same using the colorimetric scenario for all these known observed in gamma ray SBG, and we use this relation to link the star formation rate with the interstellar medium, and also this relation for putting together the star formation rate, for linking the star formation rate with the radiation. So we also check the normalization that we obtained from the colorimetric scenario with the infrared and observation that they give us the normalization of the star formation rate. And we did this for all these sources. And when we look for the expectation of neutrino for single SBG, we see that that's the one observed from Fermilab, and we see there are some interesting cases like the Small Magellanic Cloud and the Cercineous Galaxy that can be observed probably by KM3net in 1 decade of observation. So it's what we can expect, looking not only to the diffuse component, but looking at the single point sources, so at the single SBG known close by SBG actually. And it's also interesting to see what CTA maybe can see can tell us in the near future when we compare the expected gamma ray set from these sources with the sensitivity of this incoming telescope for the southern hemisphere and for the northern hemisphere. So another question that comes out when we look to these sources is what can happen if we change a bit the physics of the cosmic rays inside of the sources. So how the expectation can change if you change also the cosmic ray physics inside. And then we check just to the calorimetric scenario that we use with another scenario that comes out recently, where basically the advection is not considered inside of the core. Just that's because you should take into account how much is ionized your medium and if your medium is hot or cold. And here we report also the parameter that we use for the wind and the classical radius that we use for the nucleus of the starburst galaxies. And you see here that also changing this, it can change also the expectation at higher energy in gamma rays. And so we look how this can be important also for neutrino, not only for gamma. And here, how it changed the relation of the two scenarios, considering the gamma luminosity and the star formation rate for this object. And you see here that basically we try to do this exercise for different SBG. And you see here that basically for all of them, the two scenarios can change the expected gamma ray and at the high energy part. And we put here the expectation of SWGO, so the sensitivity of SWGO, and also we did a mock data production for the CTA. So you can see here how also this measurement can tell us much more about the physics of these sources. And so also coming back to this work that basically changing the physics and then just shutting down the advection, basically you're filling all the EGRB emission of Fermilab through the component from the SBG. And also in this slide we see how the two scenario changes also when we look for neutrino. And so you can see here that basically in the calorimetric standard scenario we use, basically we leave a space for other component for the EGRB data of Fermilab, but basically we are fitting much more. We are basically able to describe much more neutrino in the diffuse flux from IceCube. On the other hand, if you take into account the other model and you shutting down the advection in the core, you are basically saturate all the EGRB from Fermilab, and you are able to describe a much less number of neutrino from IceCube. So just here, I put a small recap of the different component that comes out putting together the AGB and the neutrino from IceCube, and just arriving to the summary. So the increasing number of cataloged SBG and the very energy gamma rays will help us to constrain more the parameter of the calorimetric scenario. And we just considering the blending and the known SBG from Fermilab, we are able to account up to 40% of the IceCube flux if we go further up to the equal 4 more or less. And of course, the new telescope will tell us also about much more information about the spectral cutoff. And we know that even though from the diffuse sky, they give an important contribution for point like, it's very difficult to disentangle them with neutrinos. we have some few cases that can be interesting, as we said, like SMC or Circinus, that maybe will be visible with KM3net and IceComm-GL2. And of course, the global neutrino network statistics and the new dedicated survey of this object from CTA will tell us much more. We will be able not only to constrain the scenario, but also especially the physics that we have inside of these sources. So yes, thank you.